Hello, everyone. We are very excited to be here with Katja Hofmann this week. Welcome to the Learning Salon. If it's your first time, the Learning Salon is a forum, interdisciplinary forum for discussing bridges and contentions between artificial and biological learning. We have obviously, oh, great, they can hear us. Perfect. And we have had a couple of weeks where we have been discussing spatial navigation in humans, in rodents, and in reinforcement learning. Now we have Katja Hofmann on a very cool talk about various new work that has been going on with her team in Cambridge, at Microsoft Research in Cambridge, in games. A gentle reminder, please ask your questions in the Ask a Question button right below here. As there's a box and you open it up, you ask your question and vote on each other's questions. If you have clarification questions, please ask your questions in the chat, and Brad is going to help out. We wanted to thank Eva, who has helped us with overcoming the technical difficulties to be here. John seems to be still in technical difficulties. We expect that he will be shortly joining us. And so with that, just remember to be mindful of each other, and we practice respectful disagreement here. So disagreements are perfectly allowed. Let's just make sure that it's grounded in reasons and we don't sort of disrespect others. There is John. Hello, John.
Hi.
It's so good to see you. Yes, we can see you and hear perfectly.
Okay.
You are right in time.
Katja, I'm really sorry. It's like this drama with me every time. I don't do it to upstage anyone, I promise. I'm deeply embarrassed, and I will make it up to you, I promise.
What about all of us?
Well, yeah, but Katja's our guest of honor.
Well, it's good to meet you, and I look forward to some good questions to make up for it.
All right, so in the way of introduction, I just want to say that, so we don't do, Katja, we don't do like formal introductions here. We try to sort of speak from experience. So I have started collaborating with Katja since joining Microsoft Research. Thank you for muting yourself, John.
I'm going to mute.
It's been such a long week.
We love you. We love you. So Katja is a very unique, I would say, leader. Very good at managing interdisciplinary people, many people, large teams, with a sense of ease and no stress that for someone like me, who is kind of like naturally a little bit more anxious, it looks like superhuman status, to be honest. It's very pleasurable to talk to Katja about science, to do science together, and we've done some work together that we've submitted, so fingers crossed, let's see where it goes. Especially, I'm excited about our collaborations because of the interdisciplinary depth of it. In Katja's team, when we send out like a neuroscience paper or a computational paper from cognitive science, all of the ML colleagues actually read it. They have very thoughtful things to add, and they incorporate it, and this is very rewarding. There is like a very rewarding interdisciplinary atmosphere that I did not personally expect to observe when I joined MSR. So I'm very happy to, I feel very fortunate to have experienced that with the Cambridge team, that you will see their faces in a moment on a slide. Katja is a principal researcher at Microsoft Research Cambridge, UK. And I will just, without spending too much time, give the stage to her and look forward to her talk, and take it away.
Awesome. Thank you so much, Ida, for the amazing introduction. I'm not sure I can fulfill those expectations that you've set, but I'll do my best. Can you see my slides? Yeah, awesome. Thanks so much for inviting me. I'm Katja Hofmann, and we'll give a talk about games as playground and laboratory for artificial intelligence. I want to start this talk by just thanking my fantastic team that I get to work with at Microsoft Research in Cambridge. Here you see us all in Teams Together mode. Sorry, Robert needs to be a little taller next time when we take the next team photo. I'm super fortunate to work with this fantastic team as part of a group that focuses on reinforcement learning in gaming. Ida mentioned the kind of interest in interdisciplinary work in our team. At the same time, our work is very much grounded in our mission to advance reinforcement learning in order to enable new applications in gaming. Primarily, that means two things. We want to get reinforcement learning and related approaches to the point where they can lead to new experiences for players. And for developers, we want to make sure that the resulting technology can lead to new tools and capabilities that empowers game developers to craft those new game experiences. At the same time, as we push the state-of-the-art in reinforcement learning in this space, as Ida has mentioned, there is a lot of opportunity for interdisciplinary work, for learning from each other and getting ideas from unexpected directions. This is a reason why I'm so excited to speak here today. I'll give you a few short vignettes about some of the work that we've done, and then I'm very much looking forward to the discussion and see what kinds of insights and maybe connections you can make. The work with my team really started about 5 years ago, and it was very much grounded in the desire to create experimentation environments in which we can push the state-of-the-art in reinforcement learning. Very much started with a game environment, and if you know anything about my work, you have probably heard about Project Mamo, the open source platform for AI experimentation that my team and I built on top of the game Minecraft. When we started this work, this was really driven by two key goals. First, we wanted to create a platform that would allow open-ended experimentation to drive artificial intelligence research for the next 10 plus years. And at the same time, we wanted to make sure that it encapsulates realistic challenges. And by realistic here, I mean realistic in the sense of what it would take to actually get this technology into actual games and into the hands of players. In about 5 years ago, we released the first result of this, Project Mamo. It's an AI experimentation platform that was built on top of the game Minecraft, and it is available open source on GitHub. So if you're not familiar with this and you are thinking about building up experiments in a super flexible, open-ended 3D environment that is fun for millions and millions of human players, then do check this out. Just to mention a few of the capabilities, with Project Mamo, we focused on making it as easy as possible to connect agents, reinforcement learning, and other agents into the game. It's very flexible. For example, you can choose different observation spaces, different action space to interact with the game, and you get programmatic control over many aspects of the environment. We support multi-agent scenarios, etc., etc. This platform has, in the last 5 years, been the foundation of a lot of research, hundreds of research projects, student projects, people learning about reinforcement using the platform. And I just want to point out two of the relatively recent efforts that have spun up on top of the experimentation platform that we initially put out. One of the, I would say, maybe most successful spin-offs is the mineral competition. This is a competition that just ran at NeurIPS in December 2020 for the second time. And it's a competition that focuses on understanding how to use human demonstration efficiently and effectively for learning complex tasks. In the competition, the goal is to train an agent to learn to find a diamond within Minecraft. And if you've ever played Minecraft, you know that going all the way through the technological development until you can mine for a diamond is actually not trivial, even for a human. Here, the competition focuses on learning this with as little human demonstration data as possible. And there have been some quite exciting outcomes of the competition already. I won't have time to go into too much detail, but in the past week, we just had a fantastic talk by William Gus and Stephanie Milani, who are the lead organizers of the challenge, give an overview talk of the latest competition at the AI Game Summit that was organized by Microsoft. And if you're interested, I can put the link to that in the chat afterwards, as this was recorded. So it's a great resource for catching up with the latest developments in this space. A second recent outcome that I want to highlight is work on multi-agent learning. So creating tasks within the Minecraft environment that can be used for pushing the state of the art in that space. There was a webinar that some of our colleagues and collaborators just gave. It's available on demand now. So if you would like to learn more about this space, then check out the resources there. Next, I want to highlight just one of the pieces of work that we have done on top of Minecraft. And this was work that was led by our fantastic former intern, Jacob Beck, who used Minecraft and other experimentation environments to understand how we could create memory models that learn more sample efficiently in a setting where there is a lot of noise. Just to motivate the problem, here on the screen, you see a simple T maze that we initially used to test out the problem. The challenge that I gave to Jake was to try and learn as sample efficiently as possible to navigate a maze that has hundreds of steps. Here you see a maze that only has on the order of 10 steps. In the beginning of the maze, the agent would observe an indicator. In this case here, it's green. When it gets to the end of the maze, shown in purple, the agent needs to make a decision. And the indicator in the beginning tells the agent which way it should turn, left or right. If the indicator is green, it goes left. If it is red, then it should go right. And so the key part here is it's a memory task in that you need to remember the indicator. It's the type of maze that's very commonly used in a wide range of experiments. In the experiments that we run here, there was one twist. One, we had a noise-free version where the agent would just step through those boxes. Version 2 was a noisy version where the observations were manipulated so that there was some injected noise. And the results were quite interesting. Initially, we trained in the noise-free version. And here you can see that an LSTM model can very quickly learn to complete this task. We also see our proposed approach here in comparison. It learns a little bit faster, but the difference is not dramatic. Now, when we put the agent into the noisy setting, so it observes exactly the same thing, but there is an additional observation that is just random noise, the performance of the LSTM just completely deteriorates. And we were shocked by the degree to which noise affects LSTM cells here. The solution that Jake and the team came up with was to augment LSTM cells with what he calls an aggregator function. For comparison, here on the left, you see a schematic version of an LSTM cell with an input. Let me show that here. An input coming in, going through a fully connected network into some kind of embedding. This is fed into the LSTM cell, which maintains a hidden state and also computes an output, which again is passed through a fully connected network. Now, just to very briefly show the modification that we're proposing, in addition to computing the traditional path to the output, Jake had the idea to split out the hidden state into two components. One would be passed through as in the original version. The other one would be aggregated so that essentially we're maintaining a running average or some other aggregate function of the input. This relatively small modification had a dramatic effect on how effectively the memory networks can actually learn. And I just want to show you some of the tasks that we run here. In the figures A, B, and C, you see top-down versions of our tasks. So starting from the simple T-maze that I showed earlier to several room tasks that Jake constructed in Minecraft. In each one of those rooms, the agent needs to turn left and right to navigate around an obstacle in the middle. It needs to pass through a door, go to the next room, etc., etc. So there is a lot of intricate short-term dependency along the way. And in addition to that, the agent has to, again, remember this long-term dependency, an indicator in the beginning, which tells it whether to turn left or right at the end. And here you can see just an example of what a successful pass through one of those rooms could look like in the Minecraft game. When we applied our approach, we again showed that in settings, even in noiseless settings, our proposed modification to the LSTM led to much more sample-efficient learning. Here you see that two variants using the average and the maximum aggregator function are performing particularly well. And we compared this to state-of-the-art approaches at the time, including LSTMs, stacked LSTMs, a DNC, and a simpler set aggregator that wouldn't be able to maintain sequential dependencies. Similarly, in a setting where we then introduce noise, our proposed approaches perform very well. Here, only the DNC is coming anywhere near the learning efficiency of our proposed approaches, but we have to keep in mind that the DNC is a much more complex model than the one that we're proposing here. So this is just one kind of flavor of the type of research that we're doing in order to improve, for example, sample efficiency or robustness of reinforcement learning approaches and related architectures. A second area that I want to touch on is how we are looking at whether and how reinforcement learning could be made part of the creative workflow of game developers and how to enable this. Here, I want to highlight a study that was done last year by my colleague Mikhail Jacob, where he looked to understand what blocks and what opportunities there might be for effective use of reinforcement learning as part of the game development process. In his approach, he conducted a survey in-depth survey with game industry professionals in order to surface challenges and opportunities in adopting recent AI technologies in game development. I will show you a very quick overview of the many areas that were surfaced in the study that Mikhail led. And I want to just take out one of these development areas. One of the key challenges that he identified was in the space of design and control. So he found that for many practitioners, a key challenge is that they have very limited control over what is actually learned by a reinforcement learning algorithm. And the perception, and maybe also the reality, is that for many practitioners, unless they study reinforcement learning approaches in detail and have really in-depth expertise of the underlying technology, they wouldn't be able to have a lot of control over the kinds of outcomes, the kinds of behaviors that an agent would actually learn in a game. To start to tackle this, Mikhail and our fantastic intern, Batu Ayemis, collaborated to try and understand what kinds of techniques could afford game developers the necessary amount of control. Here, I'm just showing a short vignette of a solution that they have developed, where they show how designers could achieve much greater control through a combination of preference-based style rewards that allow a game developer to specify how a task should be solved rather than just what task should be solved. And then combine this with potential-based reward shaping in order to create much more intuitive ways of combining those different reward functions. As mentioned, I won't have time to go into a huge amount of detail, but if you're interested in this space, then I recommend that you check out the blog that is shown here on the slide. The final and third area that I want to touch on is to look at the actual game experiences that we could enable using reinforcement learning. I will discuss this in the context of Project Pedia, which we announced about half a year ago, last summer. And you can learn a lot more about this project, again, on the URL here shown below. The key North Star, the long-term challenge for this project, is to understand whether we can train agents that can adapt on the spot to new teammates and opponents. The reason this is important in games is that when AI agents face a new human player, there might be a huge variety over the natural human behavior they might encounter. So it's a question of robustness. We want our agents to be able to respond to the huge variety of situations they might encounter in a game. And ideally, we'd also like them to be able to coordinate or collaborate in an ad hoc way with the humans they encounter in the game. So let me give you a sense of how this could fit into a game. Here we're working with a game called Bleeding Edge. This is a game developed by the game studio Ninja Theory, which is conveniently located here in Cambridge, virtually next door to our lab. This is a 4 versus 4 team-based game, and you can see some of the cyberpunk-like characters that are playing in the game. In the screenshot here, you see an overview of one of the maps. And so in this game, there are control points that are shown here in blue. There's one more here. And teams in this game really compete for control of those control points. This is a fantastic game to test out ideas around coordination and collaboration, because it's a fast-paced game where teams really have to tightly collaborate in order to gain an advantage over their opponents. In this video here, I want to show you just a short vignette of how, with current state-of-the-art reinforcement learning agents within a team actually do learn to coordinate. One of the examples that you're going to see is shown already in this picture here. So in this picture, you see that one of the players on the team was knocked out. And you see here that there's a healer that is helping the agent recover. So it's one example of how the agents can coordinate in the game to make sure that the health is recovered before the agent goes back to face their opponents. And now we're going to see a video where this is shown live within the game in the 30-second clip. So we follow the character here. It's going to the platform, trying to get control of the platform. And in a moment, you'll see the opponent attacking, actually knocking him down. This is where the healer of the team jumps in, helps recover strength so that it can go back and face its opponents. Right. We also see that the healer has learned to switch between its teammates so that it can help them recover the damage for those where it's the most important, so where the health is currently lowest. So in this short demo here, we have seen how agents that are trained together, for example, in self-play, are able to learn to coordinate effectively. However, this doesn't solve the problem that I was explaining earlier. When faced with a new human teammate, there might be a wide variety of strategies that the human players could choose. And without training with those particular strategies for a large amount of time, current agents wouldn't be able to effectively coordinate with those human players. This is where the last piece of work comes in that I want to highlight today. This is work that was led by my fantastic PhD student and former intern, Luisa Sintgraf, which was recently accepted to AMAS. The work is called Deep Interactive Bayesian Reinforcement Learning via Meta-Learning. And I want to use this simplified problem setting that you see here on the slide to illustrate the problem and then the approach that we're taking here. So in the simplified treasure hunt, we see 2 agents shown here in gray. This is the agent that we're controlling over here, and it's at runtime facing different collaborator agents. The agents that it's collaborating with, for example, here have different preferences. For example, some like to collect red coins and bring them to the red bank. Some like to collect the closest coins, and some have a preference for blue coins. The task ultimately is to collect these coins, bring them to the correct bank. But as you can imagine, if an agent would be able to predict what actions its collaborator will take, it would be easier to understand what is the optimal action in a given situation. Now, in the work here, we propose an approach that is designed to test out whether it is beneficial to explicitly form a model of the other agent's behavior. On a very high level, this is the Meliba approach. It consists of 4 components. Our agent observes the other agent's behavior and tries to predict its future actions. This prediction of future actions happens in an embedding, and we can use this embedding to summarize the other agent's playstyle and its current frame of mind. And we can then use this in order to choose our own actions based on this embedding of the other state and of our own state and the summaries of other agents. I have a little bit of time, so I can walk you through this in just a little bit more detail. I won't go into too much detail on the notation here. So maybe just to explain a few of the components. Tau here is the trajectory of our own and the other agent's behavior so far. So this is the data that our agent would observe. Oops, let's step through this. So we observe the other agent's behavior. From this observation, we try to predict all the other agents' future actions, which is illustrated here. We do this using a variational autoencoder, which allows us to capture the full distribution over the possible behaviors and state of minds that the other agent might be in. So in this this variational autoencoder, this thus creates a latent embedding that captures that full distribution. And now in our approach, we're able to feed the representation of that full distribution over the other agents types into our own policy and take actions based on that. Just to show you some of the results that we've been observing here. Here we see in purple and pink 2 variations of the approach that I have just described. And we see that this leads to very sample efficient learning in this particular game. We also compare this to RL2, which could be seen as a model-free version of this approach. And we see that RL2 has a much harder time trying to capture what's going on. We also show what happens if we just input the average as opposed to capturing the full distribution over other agents' behavior. And we see that this performs much worse than the proposed approach. To understand what's going on in a little bit more detail, we also try to predict from the learned embedding what agent type our agent might be interacting with. And if we look at the prediction accuracy of trying to predict the other agent type from the embedding using our own approach versus the hidden state of model-free LSTM, we see that prediction accuracy goes up with the variation approach that we're proposing here. So while this is still work in progress and we're building up on this, this is an early indication that forming an explicit model of other agents' behaviors and maintaining a full distribution over the agent types that we might be facing is beneficial for coordinating our own behavior with those other agents. So it's quite promising work, and I'm quite curious how much further we can take this. I also think this is an interesting area for maybe discussing connections with other disciplines. And I'm quite curious to hear what you think about what it might take in order to allow agents, biological or artificial, to effectively collaborate with each other. This was the quick overview that I wanted to give you today. It took us from the world of Minecraft to augmented memory models, to the kinds of blocks and limitations that game developers might currently face when trying to use reinforcement learning in order to craft new game experiences. Finally, we took a look at the game bleeding edge and the kinds of challenges it poses in trying to learn how to effectively coordinate between agents and eventually with real human players. And I walked you through some of our latest results using Maliba in using predictive models in order to learn more effective collaboration. If you want to learn more about the exciting space of AI and gaming, I already briefly mentioned that we held an AI and gaming research summit last week, and I'm showing the URL here. The recordings of the talks will be made available shortly, and this is a huge treasure trove of interesting research within this space. Finally, I again want to thank my fantastic team as well as our external and internal collaborators. If you want to keep up with our latest research, this is our website. With that, I'm really looking forward to our discussion. Thank you.
John's clapping.
Oh, wow.
He's just disconnected.
Oh, so many problems today.
Yeah, a little more than usual. Thank you so much for that great talk. Let me see what John... He says, I am here. Oh, apparently, well, he's not. But, okay, so we're going to try to invite John back in. And so the chat is sending you a lot of claps. I don't know if you see that.
Thank you.
We will, as usual, ask you a couple of questions before sort of we open the questions to the audience. And so first, I want to, one second, I want to first see what John is saying. Get John back in. He says, let him back in.
Yeah. Let himself back in. I invited him.
Oh.
All right.
Okay,
I'll worry about it.
Yeah. So usually he has a lot of questions about RL that we let him go first because it's like a kind of like more, and that's part of the reason I kind of want to wait for him to show up, because I'm sure that we might also, a lot of the audience might also have clarification questions just to go back and like unpack some of the slides, because you had so many wonderful things that might be new to some parts of the audience. So a lot of the people obviously in the neurosciences are familiar with LSTMs, but it's always helpful to kind of give a reminder, especially since we encourage our junior members of the audience to ask questions. So I think I will, since once John arrives. Perfect. John is back here. John, do you want to go first while you're connected? You're muted right now. You're muted.
I do want to go first.
Go for it.
Because I am definitely the very junior member when it comes to this stuff. So I can ask the questions that will help. I'll pretend that I'm asking them for the junior people in the audience, but they're really for me.
Of course.
I thought maybe it would be really helpful for you to go through that T-maze example, Katja, and just explain to the audience, because there are a lot of biologists here who don't even know what LSTMs are, right? So it would be really helpful just to explain what that is and why you had to do the aggregate memory in order to get that solved. It's second nature, but I'm sure there are people who actually got lost even at that stage. So maybe you could just explain what's going on there.
Sure, fantastic. And
if you want to put the slides back on, you're welcome to also.
Oops, let me grab the right slide first.
We pray to the gods of the internet that John's Wi-Fi is going to hold up this time.
Yeah, I don't know what's going on. I think it's Jovo broke into my house, but we'll talk about that later.
If I break into your house, it will be to kidnap you and bring you to my house so you have good Wi-Fi.
All right, so we start here.
Yes,
so first,
yes.
All right, so let me start with the task briefly, just to make sure that that's clear. So when we talk about a T-maze here, we can form kind of, for an artificial reinforcement learning agent, there are many ways in which we can represent this. You should, in the simplest possible form, we have what we call a symbolic representation. So the agent might just observe a few numbers. When I show the square here shown in green, it might observe a 1 if the first square is green, a 2 if the first square is red. It then takes an action. The action here is discrete, so it can move forward, left, and right. So here it needs to learn, okay, when I see that first number, I move forward. Then it might observe a 0, moves forward, a 0, moves forward, etc., etc. At some point, it observes the purple squares. So let's say that's another number, a 3. And then it has to decide whether to turn left or right. If it turns correctly as determined by that indicator, it gets a high reward. If it makes the wrong decision, it gets a negative reward. So that's roughly the formulation for the kind of reinforcement learning task for the agent here. We have an observation space that's initially, let's say, symbolic, just a number. We have an action space that consists of 3 discrete actions, and we have a reward signal, 0 along the way, and then positive or negative, depending on whether we make the right decision. And so the task is set up in this way so that we can test whether our artificial agent is able to learn a long sequential dependency. So the length here is how many steps there are in the maze before I reach the final junction and have to take the action that is determined by that initial indicator. And so we can set this up to be arbitrarily long. We could make this maze 100 steps long and make this task harder and harder to test out how our artificial agents are able to pick up on those sequential dependencies. And now, in terms of the model that we use, kind of standard model or standard architecture for learning these kinds of sequential dependencies, is what's called an LSTM cell, which stands for long short-term memory, and was initially proposed by, I have the citation on the next slide, by Hochreiter and Jürgen Schmidhuber in 1997. I'm leaving out here a lot of details of what's inside the LSTM cell, but it's an architecture that consists of several components. In particular, it has a number of gates, and those gates determine whether information should flow from the past to the future and what information should flow from the past to the future. The way the information flows is indicated by this H here, also called the hidden state of the cell. So whenever we kind of compute the function that's currently captured within this LSTM cell, we take the hidden state, so let's say a vector of numbers passed from the previous step. We take our current input, so that could be just our symbolic observation, the number that we observe about where we're currently in the maze, or it could be some embedding of an input. So it's some vector of numbers. The LSTM then computes a function of that current input and the history. And so by learning a combined function of the current input and the history, the cell can in principle learn to memorize important events that occurred in the past. And when it computes its output, in our case, the action that the agent should take at this particular point in time, this function can then be a function of everything that the agent has experienced so far, as well as the current input. Let me check with you, John. Is that clear so far, or do you have any?
Well, I mean, I think I get what the LSTM is,
yeah,
but maybe you can now explain why we need it for your T-maze.
Right. So in the T-maze, at any given point in time, the agent only observes the current state. So let's say if it's halfway through, if we're in the symbolic space, then it might just observe a 0. So in order to remember the initial indicator, it needs to have some way of computing functions that take into account the entire past interaction history with this maze. Otherwise, when it gets to this purple function, it has no way of knowing whether to turn left or right.
So it's basically just to prevent amnesia.
Exactly. Many kind of artificial reinforcement learning agents don't use any memory at all. So that means they really just have some kind of function that computes some function of the current observation, a current image, or whatever that current observation is, and then it takes an immediate action. So with that, you get a policy that can only react to what's currently right in front of the agent. To go beyond that, LSTMs are the most common, or the standard choice for current agents, I would say.
That's awesome. Okay, so when do they fail?
When do they fail? Okay, so one test, and what we thought was a simple modification of this maze, is that the agent might experience noise in its observations, in its environment. For example, when we have visual observations, those can be very noisy. And so what we wanted to test out is what happens when the agent doesn't observe that very clean input signal, but there's also some noise in its environment. The way we first simulated that in the simple T-maze is we just added to the agent's observation an additional variable that contained random noise. So it was just sampled from, I think, 0 to 1 or something like that, and added to the observation. And this simple modification caused the agent to completely fail when it was learning with an LSTM. So noise had a very, very strong effect, even though the task was the same action space. The observation space was one additional field in that observation vector, and the reward signal was exactly the same.
So is the intuition, Katja, that they don't have any taste and they just remember the noise just as much as they do the important stuff?
That's one way to interpret it. It did show us that this kind of classic approach, classic as far as the 90s go, is not very robust. And when we think about real world scenarios, noise is kind of the first thing that can come up. And noise is actually, should be something that is quite lenient or should be relatively easy to deal with. And here we saw that even with this very simple modification, the agent just completely fails to pick up the signal from the noise that is observing.
Mm-hmm, mm-hmm, mm-hmm. Okay, and then you had to add something even more long term to solve that other thing that you had.
Right. So exactly what we propose here is a simple modification to this LSTM cell, where we wrap it with what we call an aggregator function. So instead of if we look at the comparison here, instead of only using the hidden state to kind of maintain history, pass on to the next time step, we use the H vector here and split it up in two ways. One path is the normal path that would be taken by the LSTM. The other one is a path through an aggregator function. And so this function simply computes a running average of everything, all the hidden states that the agent has observed so far. So what we're doing is we're building in a simple inductive bias that makes it easier for the agent to compute a function of the current input, the history, and an aggregate of the history. So an aggregate of everything that the agent has experienced so far. And it turns out that simple modification is very powerful for recovering, for example, from these noisy settings.
I see. So I was imagining that that funny maze that you showed, where there are a series of rooms, was the reason why you needed the aggregator, not because of noise. Or is that another reason you need the aggregator?
Right. So the initial motivation was just in the noisy maze, but then it turned out even in those funny rooms, the aggregator leads to much better performance. And we have some explanations for that. We find that the augmented with the cell with the aggregator achieves a much higher signal to noise ratio, which is expected, but we can confirm that experimentally. And it leads to much stronger gradients as the agent learns in this scenario. But so to look at the funny maze here, in the tasks that we're giving those agents, the rooms there are many more rooms. So here we're just showing an example where there are 3 rooms shown over here. Typically in our experiments, the agent would have to solve 16 rooms, one after the other. And so in each room, it has to walk around the obstacle in the middle, go up and down in order to go to the next room until it finally reaches the end. And then the long-range dependency is exactly as in our T-maze. At the end, there is a junction, and the agent has to take the right action depending on the indicator that it saw in the beginning. I admit that walking through 16 rooms like that in Minecraft might be a bit boring for actual humans, but technically it's something we could do. For our agents, luckily, they don't get too bored of this task.
So Katja, is the intuition why the solution to the noise problem faced by the LSTMs and the fact that it worked as well for these rooms that sort of have this subtask that you have to solve along the way to the end, is in a way, could you consider the subtasks a kind of distraction that you mustn't allow getting in the way of the real goal? And so it's a kind of pseudo noise. Is that a way to intuit what these subtasks are?
Yeah, that's a fantastic intuition, and that's exactly how we set it up. So we wanted to craft a task where there's lots of tedious short-term dependencies that the agent just has to deal with, but in the middle of all that, it needs to keep the longer-term goal in mind and make sure that it learns that really long-range dependency that is responsible for a very strong reward signal.
So that's fascinating. So, I'm actually trying, I have a little video game company and I'm really interested in devising video games. And so I find the whole world of video games deeply interesting, right? And But I wanted to ask you a couple of meta questions now. In other words, going all the way back to, Wittgenstein, who said it's impossible to define a game, right? But we kind of know a game when we see one, right? So I was wondering, do you think that games, and I think games are all about, winning and losing, rules, opponents. In other words, there's something about a game. I mean, life isn't a game, although people say it is, because there aren't rules to life, right? Of course, religion tries to impose them, but, do you think that one of the definitions, I was thinking that if Wittgenstein was still alive, I would have answered him and said, based on Katja Hofmann, that the definition of a game is something that can be modeled with reinforcement learning. So do you think that there's something about the gaming environment, even the amazing, more complicated multiplayer games that you're starting to model, that there's something about games that makes them really, with ingenuity of people like you and your team, that it can yield to a reinforcement learning algorithm? In other words, is it something about games? Do you see what I'm saying? In other words, you've discovered a deep truth about the games that humans play, that they can succumb to ingenuity in the reinforcement learning community. Do you see what I'm asking? I'm probably sounding
I think I see what you're saying. By the way, did you know that Wittgenstein is buried just a few kilometers north of here, about 2 kilometers north of here? So I feel quite close to him, deep in my heart.
So he's listening, Katja.
Maybe. Right. But I get what you're saying about the language games that he described, and the fact that you wouldn't be able to put your finger in it. You wouldn't be able to explain the rules, but people know it when they see it and they can play it, and language emerges from the games that people play and the meaning in a way that they give to them. But I think you're asking something that is quite techno-optimistic about reinforcement learning, and I do not subscribe to that view. I believe that if at all possible, it will take a very, very long time indeed until everything that we call a game succumbs to reinforcement learning. I do think that games are a really interesting way of teasing out very interesting aspects that we want to study. So for example, in a game like Minecraft, I can have a human player and an agent almost on an equal footing. They can observe the world from, let's say, the video image of the first person view, which is much more similar to how they could observe many other real-world environments. So we can align things in a certain way within a video game. At the same time, the complexity that you can see within a game is open-ended. And one reason why Minecraft is so fascinating to me is because it exactly provides this ladder, right? We can study simple memory tasks like the one I just described. But if we ever solve, for example, multitask learning within Minecraft, we can always put human players in there, and the complexity of what a reinforcement learning would have to deal with is all the way up to human psychology, human social connections, collaboration. And so to me, games are really a way of trying to slice and dice some of that complexity without getting rid of the important parts. In the long run, my hope is that we can kind of use games as a platform for testing out some of these experiences, because people can have such an kind of immediate experience of that game environment, right? It feels real in many ways. It's immersive. So we can try out a lot of things that we wouldn't be able to try out in the real world. But kind of proposing that reinforcement learning agents would be able to capture or deal with everything that happens in a game, that's really long out.
Sure. So but do you think then, I mean, it seems to me that your gaming universe is like a laboratory for exploring
exactly
how you can slice and dice things. But are you saying that not only will you find ways to sort of match human players, but maybe you'll begin to get some more formal sense of what extra will be needed to do those things that you think will not be. Do you have some sense already, I'm putting you on the spot, of what
No
you're
worries.
going to have to add, or what you think where it will fail? I mean, do you have some sense of when it's going to do well in a game and when it won't? I mean, have
Right.
you got some intuition about that?
I mean, there's a clear place where it's going to fail, and that is whenever some information from outside the game environment is necessary. So to the degree where we can restrict, for example, decision-making tasks to everything that an agent could observe or in some way experience within that closed world of the game, I think we can be quite effective at that. But in many cases, games, they're really interesting relationships to the real world. We transfer our knowledge from the real world, from all the wealth of experience in a normal human life. And capturing that is impossible unless you somehow build that into the algorithm from the very start. So I think a game, it's closed little environment, it's universe, and we can study interesting effects and relationships within that closed universe. And we can put people into that closed universe. So that's why it's particularly interesting. At the same time, there will be a lot of things that can never be captured in there.
Yeah, it's really deep. I mean, it's just so interesting. And I just wanted one last question, honestly, because it's I'm just warming up.
Fascinating questions. Keep going.
The Aliba part I found really interesting. And I was just trying to decide whether it was an agent with human qualities, or whether, for example, you had modeled the landscape. So it was every now and then an earthquake would happen, but the earthquake had some structure to it. There was some distribution to, the ground under you suddenly falls away. Or it seems to me that if you were to model that sort of earthquake feature, that wouldn't be that different from an agent, right? In other words, it's not really about psychology, right? It's about some kind of predictable distribution of behaviors, right? Is that fair to say? That it's not, you call it an agent, but the weather could be an agent within this way of thinking. So it's not psychologically special to call it an agent. Is that correct, or am I getting it wrong?
Right. That's a fantastic question, and I'd love to hear your thoughts on that as well. In many ways, you're absolutely right. We, in this particular game environment, give special kind of attention to whatever it is we call an agent. And in a way that is just a function. There's a distribution over it. It's relatively consistent within a given episode, and then it can change over the course of episodes. So other events, earthquakes, as you mentioned, or other shifts in distribution could be modeled in exactly the same way. At the same time, and what I'd love to hear from you about is, I don't know what makes kind of, let's say, our perception of other agents so different from that. And I'd love to kind of long-term get a better understanding of that, right? What might be the minimal components that we need in order to model what we do, in order to, for example, am I currently predicting your behavior? Do I need machinery that is different from predicting other natural phenomena? What makes it so different for me that, I model you as an agent? I'm curious.
Yeah, it's really no. I mean, look, I'm extremely flattered that you even deigned to think that I would be able to answer that question. But it's just, you got me thinking, right? That, what is the difference between an agent and an earthquake, right? And and I wonder whether one of the things is that, we are probably, as human agents, sort of meaning. We're fueled by meaning, right? In other words, like you were saying, we have knowledge as humans, and you have knowledge of what we are likely to have knowledge of. And therefore, you're going to have this extra thing, which is that you both, as humans, share an Umwelt, or worldview, or knowledge. And that's something extra that you can bring to bear, that isn't just a kind of modeling of an inanimate phenomenon. Do you see what I'm saying? Now, we always talk about people wrongly anthropomorphizing the inanimate world, right? And so maybe we should not ascribe agency to the weather, but of course, the gods of the weather have been. So in other words, I think what's really deep about this is you could begin to see when, based on the behavior either of the game, the reinforcement learning agents or humans, when they start to imbue psychological motives and meanings to the agent and when they don't, right? There's something very deep about this, right? I mean, it seems like you've created a lab that can do all kinds of interesting stuff, right? I mean, it's just fascinating. I'm just getting a little bit of intellectual vertigo thinking about it all. I think it's amazing. I mean, thank you very much. It's a lot to think about, but I'll stop prattling on so that the others can ask questions.
Thanks so much. Very thought-provoking.
John, we would be happy to give you more time to ask questions. We're not running behind time this time.
No, I did have one last sort of very dumb question, which was about latent embedding. I was wondering maybe, could you just give us an intuition of what that means when you say that? It seems like almost like a compression of the memory for use. And is that kind of what that means?
Right. So we use latent embedding really as some representation that is usually not observed. So in the memory cells that I mentioned, there might be something that is hidden, and it's very technically it's a vector of numbers. So it's a compressed representation in the memory cells of the history of the interaction with the environment. In our model of other agents, it's a representation of the interaction history with the other agent. So yeah, it's a compressed representation.
All right. Thank you very much. I cede the floor to the Honorable Ida and Jovo.
Thanks so much, John, for your amazing questions.
Jovo, go ahead. John, by the way, I really enjoyed that. And I think I'm glad that this was recorded in which you were the techno-optimist.
So, thank Katja.
I can say one thing, Jovo. Yeah. One thing I can say is, it seems to me that Ida always manages to find the one thing that I know I said that I will regret later.
She's deeply insightful in that way. In many other ways also.
Yes, she is.
Okay, so thanks so much. I wanted to echo some of what Ida said earlier. Is your career is just so impressive in terms of your ability to come up with really cool new algorithms and also like build actual systems that you and others can play in. There's such different skills, and you do both of them so well. It's really impressive and aspirational. So
thank you.
That's cool. My questions were really very closely related to John's questions, actually. So we may have stolen the show already. What I was going to ask, and maybe there's a little bit of a difference, is we've talked a lot on the Salon about learning in general, and artificial general intelligence and human-like learning, and reinforcement learning has come up in many contexts before. But what's different about what you said and what everyone else said is you really focus on games. So not reinforcement learning in general, but I'd say more of a focus on games, and reinforcement learning is a tool you're using, but the link to your lab is a game intelligence, not, well, I guess you have a reinforcement learning link too, and a game intelligence link. So, but I guess, yeah, so my question is what specifically about games do you think that we can learn that using the same tools of reinforcement learning we wouldn't learn without games?
Very interesting question. One take on that could be, in many of the past presentations, even in Hugo's presentation last week, games have featured very prominently. So there must be something deep about games that allows us to study phenomena that might otherwise be inaccessible. One motivation for me is the human. It comes down to the human aspect. If we want to collect data or get an understanding of how hard would a task be for an actual human, games are a really, really good environment to try that out. Ideally, those games would be fun and engaging in some way, but typically we can set up games in such a way that it's not just a kind of repetitive, boring task or experiment that the person has to go through. But if a game is set up right, then they're fun, engaging, and then there's kind of a meaning, as John said, to playing the game itself that in a way takes people away from having to prove something or demonstrating this memory task. It's part of being immersed in the environment. They do whatever it is they want to do within the game. And this allows us to get quality and depth of data that I think would be otherwise impossible. So, for example, when we work with the Minecraft experimentation platform, in many cases, I was able to say, hey, maybe an intern or collaborator has set up a task, and the agent wasn't able to learn the task. And in Minecraft, you can go, well, go try it yourself, see if you can actually solve it. And that's very powerful. We found a lot of bugs by actually going and playing the task or playing the game by ourselves. That's one aspect. It's also related to kind of my long-term aspiration, the kind of experiments around genuinely putting reinforcement learning or kind of agents that resemble reinforcement learning agents into a shared environment with human players and testing out what kinds of interactions might be possible. I find that really fascinating, and I hope we get to that point at some point.
So let me see if I can summarize and see if I got the basic gist. Basically, if I'm right, you're saying that we're all studying learning. We have to choose an environment in which to study it. And games have this very natural, nice balance of motivation, control, and flexibility that just creates a really good environment to study the things.
Yeah, that's a fantastic summary. I might quote you on that.
Okay, cool. And so the other question I have is, they do seem really powerful. And so I wonder, John alluded to, he has this company, a startup that does games. I wonder, in your view, what are the short-term, real-world use cases for using gaming to improve our lives? I can think of various things like better automated testing or assessing for cognitive disability or physical impairment or therapeutics, but I don't know anything about those things. So I wonder if you have an informed opinion about that.
Right. So you're asking whether games and the new experiences we could create would be beneficial in some way beyond the play.
Yeah.
Right. I would say that games are beneficial in and of themselves, especially in times like this. They're a way for people to maybe leave behind their day-to-day troubles and escape for a moment, or to play with someone, connect with a loved one, or even socialize online and find friends. And our colleagues from Xbox are telling us that in this time, people definitely turn to video games more than they did before. So you can see this effect. So I would argue that there is a really strong thanks, Ida, for that. Yes, a third of the world population plays video games. So if you can impact on that scale, that is really powerful. And giving people something new, exciting, maybe thought-provoking in that space, I think that is a really worthwhile goal in and of itself. At the same time, I do believe that there are applications that go beyond those applications in games. If we think about future potential real-world uses of, let's say, reinforcement learning, right? Let's say home robotics becomes a thing at some point. I'm pretty sure we want to test out how we interact with a home robot in a virtual environment first, before actually deploying that in a real-world scenario where the damage of something going wrong could be much more serious than maybe just a spoiled game session.
Yeah, that makes sense. I just want to say, I totally agree with you on your first point also. I mean, just for a really anecdotal thing, my son sees me on my computer all day long. He's 4. I try to get him not to use the screen, but I feel like a huge hypocrite because I'm on it all day. And so what we do instead is we play video games together. And it's so much more beneficial to him, I think, than him just watching Gabby Cat or whatever he would watch otherwise. So I'm a huge fan of games for those reasons also. So, okay.
There's also a reason that, for example, Minecraft in particular is so popular with hundreds of millions of players. It's open-ended. There's a lot of this emergent play rather than the game with specific rules, where people can be creative, explore. So there are many different types of playing, and a lot of that can be done in those virtual environments.
Cool. Thanks so much. I really appreciate your answers.
Thank you.
Thank you, Katja. And thank you, Jovo, for your questions. It's 5:14 our time, so I guess it's like 10 your time. It's getting so
I should get the drink now.
Yeah, please.
You're still in the water. No, it's okay.
So I really appreciate the conversation that you had with John, and I wanted to sort of perhaps go a little bit in the direction of things that you were mentioning, the sorts of things that might not be, we may not be there yet. So there are a lot of games that you cannot define the goal beforehand. And they're just like, there's so many things to explore and figure out along those games. And I wonder whether, so they won't have tags for rewards. They won't have in the same way that you might have in other places. And the goals are not clear from before. And people seem to really enjoy this, especially people who have gamed for a long time. They particularly love these. And in life in general, like some of us really like adventures or going to new territories, learning new language, doing things that we haven't done before. And we don't even know what the rewards are yet. Like that happens a lot. There has been some development in reinforcement learning in the past years for curiosity-driven explorations, for various levels of intrinsically motivated behavior, for skill learning, for various kinds of self-play, various kinds of things that are not in themselves rewarding in the basic sort of 1950s version of reinforcement learning, but they are sort of the advancements of reinforcement learning. I wonder whether we are in for another evolution of it, where it would have some other kinds of, every architecture would have some kind of internal life for that would enable that sense of exploration without knowing any goals or without knowing rewards in a better way than what we have now. So I'm asking maybe a little bit more of a speculative science fiction question about what you think would happen in the next 10 years to the sorts of agents that can explore the kinds of games that are open-ended and that are, for some reason people are talking about Bitcoins and GPUs, right? I'm
crazy. How did that happen? Talk about curiosity.
Invented Bitcoins. Like I don't know what's happening in the chat. Yeah, so I look forward to hear your response.
Yeah, fantastic set of questions and speculation. As you mentioned, it is a topic that is hugely fascinating. We've seen a lot of work in this space over the past few years. I myself collaborate with Pierre-Yves Oudier's group at INRIA. So he is kind of very, very strong. His whole group is very strong on this kind of self-directed learning. We look at things like automated curriculum learning as one of the potential techniques to figuring out what that extra that you mentioned could be. But I think there are huge open questions on what this is going to look like. When I talk about reinforcement learning, I always kind of want to put an asterisk there because I believe it's going to be a strong component of any such future iteration, science fiction iteration, as you mentioned. But I very much believe that it's probably not going to be just reinforcement learning, and it's definitely not going to be a single reinforcement learning agent just within that single environment. What that extra is going to be, your thoughts around self-play are really interesting. I think kind of just interacting with other agents or other mechanisms in some way can be a really interesting driver of that kind of exploration process. I'd love to get to the point where our agents can learn quickly enough so that it's meaningfully possible to put them into an environment that is shared with human players, to try and get some kind of back and forth, some kind of learning within that space between human and artificial agents. We're still a little bit away from that. I'm hopeful about maybe meta learning. So there is an interesting trend on trying to at least outsource a lot of that really sample intensive learning to essentially pre-learning over a really wide range of tasks. And as we broaden that distribution and the notion of what a task is, maybe that can roughly get us to the point where the learning behavior of these agents would be starting to be fast and interesting enough so that it makes sense to pair them up with human players. I think ultimately to really like a really big breakthrough would be if agents could start to learn on those kinds of timescales so that we can get interesting interactions and back and forth with human players and generally humans in the future. So yeah, my agents are very social, my future agents, not the current ones.
That's a fantastic response. And while John is experiencing further technical difficulties,
John asked his question, so he's satisfied now.
Well, no, he always gets involved in the further discussions as well. So I don't want him to miss this. So that's great. So learning on fast time scales so that the back and forth can happen, but also maybe learning a lot already offline so that the agent comes prepared, so to speak.
Mm-hmm. Yeah.
Do you think that reward-based reinforcement learning, as opposed to maybe kind of putting some of that weight or allowing some of that weight to be lifted by some other intrinsic aspects of the architecture, are going to be more likely to be in the future? Specifically, I wonder whether the reward optimization might be limiting with regards to especially situations where exploration is not part of something. It might be like all of it, or it's constant.
Right. I think it's a really good question. At the moment, I think reward optimization is the best we have. We can understand it to some degree and make progress on it. One way to sanity check could be to see, where does our learning motivation come from? Can you find a reward structure that might express that in the long run? If we really study this well, could we tease out what components go into a human reward signal, or would we discover that there's something that just where that just isn't enough? You could try from a first hypothesis and say, well, there is a lot of reward in human learning. The kind of desire to get rid of hunger, so food, there's a reward to that. Lots of social reward, right? Humans are very much primed to learn from. Well done. There's a huge amount of things that you could potentially capture in the form of a reward signal. So I think it could be a good program to start from the hypothesis that we can capture everything as some kind of reward signal, and then see where that breaks down.
Thank you. I think that was my my question from the based on some of the conversations we've had in the past sessions, and I really appreciate that response. John, do you have something else before we invite Sarah Wu and Brad on screen and ask other people's questions? You're muted, by the way.
I do think this is really a deep question that, is I think the Learning Salon one day will write it like an article and have everyone in to discuss this. I think it's really.
Love that.
I think it really is, and so maybe just what does it mean? Yes, a lot of learning is reward based. I've said on this salon many times, that sometimes, and we had a drunken Tim Behrens on the other night, and we were talking about, the difference between, which is wonderful, by the way. Look, a drunk Tim Behrens is better than a lot of sober other people, right? But
including a sober Tim Behrens.
Better than a sober Tim Behrens, right. But we did get to the idea of, open-endedness, right? Which, ambition, the desire to go to college or be an actor when you grow up, right? And the steps you need to take to become an actor. Do you think that these kind of things, sort of like I were getting at, that are we going to be able to find latent reward states that we can point to that are along the way, like stepping stones to be an actor, or are we going to have to come up with a different framework to run along parallel with it? It's what this discussion is about. When does a game become a career? Right? I don't want to just be good at video gaming. I want to be a video gaming champion, right? Is the desire to being a video gaming champion different than whatever you need to do to be good at it within the game? Do you see? In other words, that's, I think, at the heart of all this. Is it qualitatively different, or do we need to tweak what we already have?
Right. So maybe from one side, I haven't seen a strong or an argument that I found convincing enough that it's different, right? So you could say someone who goes to become a world champion on a particular game and particular esports discipline has received a lot of reward along the way. So for example, whenever they got a high score in the game, they might have experienced that as a positive reward. Once they started to beat everyone else they were playing with, they might have received a lot of admiration. So some social signal that, again, could potentially be expressed as a reward signal. And they, maybe continue to win, or they might work against imagined goals, right? So but is this notion of, I'm imagining that being an actor might be something appealing. There's a very long time scale, but still that kind of imagined reward might take a similar function to the kinds of reward signals we put our agents. I'm not quite clear on what that qualitative difference would be. So, from my hypothesis point of view, I would go with, so far we might be able to express all that as a reward signal. Very complex one.
And for the long-term trajectory, you can ignore the noise if you add something to the LSTM. No.
Exactly. Now we can learn 200 steps sample efficiently. So,
So 2 million steps is just a few more memory modules.
Right. So just the last question on this note, this is, I don't know what number Salon this is, but it's been going since July, right? And these back and forths have been what people have really liked the most, right? But do you think that the joy of debate and argument is also a complex reward function? Do you think that's possible?
Let's think about this. I'm definitely experiencing a positive reward right now. It's fun. I don't know how you would express fun as a reward signal, but there's definitely it could come back to a social function, right? So there's the joy of exchange, of bouncing of ideas with someone else. Formalizing that as a number, I don't know. That might be hard, but I'm not convinced that it's impossible.
And is it possible, even if there isn't an obvious thing to, like Ida was saying about goals, there's a difference, right? And correct me if I'm wrong, between saying, which I agree with, that there are rewarding, pleasurable aspects to this. You're absolutely right. But that's not the same as knowing what to optimize for, right?
True. Yeah.
So do you think it's not so much that I deny pleasures, rewards of this, but I don't think we know where we want to get to at the end of the salon, right? So how do you do something that's pleasurable without optimizing for anything at the end?
Right. So one possible answer could be that I've been in similar situations in the past. And, some of those exchanges might have gone better than others. Through each of those, when there was a momentarily awkward situation, I might have back-propagated or whatever algorithm my brain uses in order to tell myself, okay, I'm not going to do that again. And slowly learned from that, right? So in a given situation, I haven't been in exactly this situation before, but there have been many, many similar ones. And we could argue that it's a matter of figuring out how to learn the right representation so that in that space, situations that are meaningful to this one are close so that I can draw on that past experience. And rewards, there definitely were some in the past, good and bad.
Yeah.
What I want to add to that is this thing that, so John, in the example you provided, you said that there is some pleasure in the back and forth. So optimizing for that is something. You said that the audience does enjoy that part that, okay, John is gone now. Wi-Fi problem. But
I can see him.
I can see him.
Oh, you can see him? I can't see him, actually. That's funny. So one thing that Elizabeth mentioned in the chat is maybe reward changes the observation space. And I think that that's very interesting. Because to add to what we were saying earlier.
Mm-hmm. Yeah, that's a very interesting thought, right? So if we just get a sense of the scale of, right, for our agents, we give them a number or a small vector at a time. For humans, I believe there are millions of signals that bombard our brain in a given second. And somehow we need to figure out how to get through all that noise and focus on what's relevant to the current situation. So, I mean, some rough models of attention exist. I think there's a lot more to understand and how that might combine with past rewards, expected rewards, and how we make sense of a situation. So, yeah, I agree. That's a really good thought.
There's one other thing I wanted to add to that, and something related to what John's question is, not all algorithms actually optimize anything explicitly, and this is true in general and in AI. So my favorite example of this is self-organizing maps, one of the oldest AI algorithms, and you can prove it doesn't converge to optimizing anything at all in particular, but it still learns structure in the data very well. And so we don't need to know what we're optimizing for to be able to identify useful structure.
Yeah, I definitely agree. So, hello, Sarah Wu. Thank you for joining us. And yeah, please go ahead and ask your question and feel free to introduce yourself, etc.
Hi everyone. I'm Sarah, and my question is about creating good opponents and good teammates for agents. Can agents compete with each other to learn to be good opponents, and can they work with each other to be good teammates?
That's a fantastic question. And it is something we have studied a little bit in my group. I don't have a huge amount of expertise there, but it seems that learning to be a good opponent is actually easier than learning to be a good teammate. So for opponents, well, we've seen empirically there has been a lot of progress on training good opponents for games like chess, Go, and many other games. And often you can have some form of self-play recently, where you pitch a variety of opponents against each other. These games are typically zero-sum games. So when you discover a better strategy, you immediately get a reward signal. You have an advantage over your opponent. So the opponents can kind of push each other towards finding the solution to that game, the equilibrium strategy, until there's no improvement possible for the other agent, or for themselves, for that matter. For collaborative tasks, it's much harder to understand what you should be optimizing for. So even that is not necessarily clear. So, for example, do you want an agent within a maybe collaborative setting to optimize some kind of shared reward signal? That's possible. In most kind of game settings, we actually have a mixed reward signal. So there's some component to individual reward. If I kind of achieve a goal in the game that's good for me, and at the same time I want to make sure that my team wins. So it's a general sum game, and the reward structures there can be very complex and very hard to optimize, even starting from attributing reward. So if my team does well, is that because I've done something good, or because there was another player on the team that is just able to compensate for my really bad behavior? There's been some really interesting work, for example, out of Shimon Weissen's lab to try and study how we can learn better credit assignment in those, first of all, in fully collaborative games. But as far as I know, doing this in the general sum game is a completely open, is an open question.
Make mistakes and somehow the team works perfectly. So
that must be because of our mistakes, right?
We don't know that. It could be that we all adaptively sort of compensate for any minor issues. So.
What are we optimizing for?
We don't know yet. Apparently for enjoyment and learning.
Love of the world.
That's a good response. Thank you very much.
Thank you for
so
the question.
Do you have a follow-up or?
Not really.
Okay.
Thank you.
It's nice meeting you.
Nice
Good
meeting
meeting
you.
So Brad is here from his very real 80s background.
Wow, that is fantastic.
He has 60 kilobytes of RAM, apparently. Go ahead, Brad.
Yeah. So that was a really interesting talk. Thank you. This seems like a really exciting, way to push things forwards that, intersects with the research side as well as the entertainment side. Minecraft obviously has a free play option. And I was wondering, well, at first I was wondering, have you gotten agents to do interesting things in sort of free play mode when there is no kind of objective function? And then that got me thinking, well, why is it that humans do interesting things in sort of free play mode? Like, do we genuinely operate without a sort of objective, like when we're just like playing around and building whatever we're building, or are we setting sort of goals for ourselves along the way to sort of power those little sort of bursts of creativity? And I was wondering if you had any thoughts about that.
Fantastic question. So we haven't set up our agents to run around without any type of reward signal. At the same time, they have learned things that were interesting. For example, we set them up in a Minecraft arena where they were supposed to fight mobs, zombies, and other things. And some of the interesting things they found to do was that in the whole arena that we had set up, there was one cube that was destructible. So the agent figured out what that block was. It learned to navigate the zombie to exactly that block so that it would blow up next to the block, creating a hole in the world that it could then fall through and run around happily ever after without ever running into one of these stupid zombies again. So it found a way to maximize the reward structure that we had given it to survive as long as possible, but in a way that was definitely not expected by us. Now, we can kind of explain all that by reward-driven learning. At the same time, it's surprising to us. So I don't know kind of where exactly we would draw that boundary between kind of, I don't know. It's not creative. There's a very clear mechanism behind it, but it is very interesting for a human observer. In terms of humans playing this, I think we should ask someone like Alison Gopnik, someone who understands that drive in children to do interesting, fun things. I certainly kind of don't know the answer. When I go into the Minecraft world, I personally set myself goals. I like to build tree houses. That's usually when I go into a Minecraft world, that's one of the things I do. And there's kind of one aspect of Minecraft that I find fascinating, redstone, which kind of works like electricity. You can build machines and circuits and things like that. And I kind of try and figure out what kinds of mechanisms I can build in there. It leads to unstructured play. At the same time, I do think about it in terms of a goal. Let me see if I can do this or if I can do that. I don't know, where would that get us? Is that completely free, or is that goal or reward driven?
But Katja, just so I don't lose my, when you say, I agree that once you articulate it overtly as a goal. What would happen if I did that or did that? But where did that idea come from in the first place? Right? I mean, once you've had the thought, what would happen if I built this? Then at that point, going forward, you can cast it. But where did the idea in the first place come from? How do you cast that in a reward-based framework?
Right. Social environment could be one aspect, right? I've seen others do it. I've seen others get positive reward. Hey, this is cool.
But you know what you're doing? If you start formulating it that way, Katja, there's no such thing as originality, right? There's no such thing as a new idea. Everything is just a version of something that came before it. It's a bit depressing if that's what we end up turning everything is a version of something before, right?
Yeah. What would an entirely new idea come from? It has to be grounded somehow in our experience, in our life.
Yeah, I mean, I think there's a good argument that the vast majority of creativity is, remixing things that we've already experienced in slightly different ways, and there's a strain of thought that is a sort of large part of what creativity is all about. You pulling up memories from one context, applying them to a different one.
Yeah. The agent finding that one stone to blow up and jump out of the world, right? To us, if you don't know the underlying mechanism, it could be seen as interesting, creative. Underneath, I know the very mechanistic explanation for it.
Right, but I just find that then the problem with that is a little bit like evolutionary psychology. Then whoever invented Minecraft, it was kind of inevitable based on their past experience that they would invent Minecraft. It begins to be a little odd if one starts to say that there was something inevitable to the invention of Minecraft based on their past experience. It was.
Are we getting into a free will debate?
Yeah, free will again.
John, it doesn't have to be deterministic. I mean, there's stochasticity in the dynamics.
Right, but that still implies that anyone could potentially have invented Minecraft.
With different probabilities, I think that's true.
Yeah, but you see, that kind of argument to me is unbelievably deflating.
I'm sorry for your ego.
It seems a realistic explanation to me. I don't know what would that spark of something outside. What would that entirely new idea? Where would that come from?
Well, I mean, it's just a very interesting argument. It's like evolution, right? On the one hand, you get descent through modification, but you also get these emergent events.
I think evolution is a fantastic example, right? There's no direction per se. At the same time, there is a fitness, right? There is a mechanism to it. If you knew all the pressures in a given environment, you might be able to predict what would happen. It's relatively simple rules. At the same time, they give rise to this amazing emergent complexity, right? To us, it's fascinating.
Sure, but Darwin himself, when thinking about the brain, said it's very important to not conflate the story you tell about how you got to it versus the story you tell about how it works. And so it seems to me that one mustn't conflate the learning story with the steady state performance story, right? So yes, right? And actually Darwin literally writes, I have no idea how the brain works, but I could tell a story about why you got one for adaptive reasons, right? So and we have to be careful not to conflate those two stories. Wouldn't you agree?
Absolutely, I would agree with that. My argument is more that there are processes that eventually that are amenable to scientific study, to potentially understanding and explanation.
Yeah. No, this is the heart of the Salon. I mean, this is, I struggle, it's interesting that for me, and it could just be, what Jovo said, it's just ego on my part. I hope not. That I don't have a sense of satisfaction yet that it could be what you're saying, right? I feel like it's not fully satisfying yet, but it's a great story, right?
It's been 5 months of us trying to clarify things.
Yeah, I love the way it's called. I love the way it's called clarification, as in we know the truth, you don't.
I'll have to go back and watch all the predecessors.
There is a lot of off-screen discussions that you have missed also.
I have to catch up with you on that.
I want to follow up on what the thing Katja said in response to Brad's comment, which is this perfect example of evolution where there's literally nothing that's being optimized. No one is asserting a goal. It's just not there. And it's a perfectly fine learning system that achieves objectives from our perspective and adapts to the environment. And I don't have any particular good reason to think we're not the same thing as that. Like, there is no objective. We're just changing in response to the environment and stochastically so that we can come up with new stuff, even though maybe John can't, but others can.
I'm interested there, right? You note there's no objective, and I agree there's no overarching objective. There's no kind of imposed kind of reason for evolution to turn one way or another. At the same time, you can see it as locally optimizing, right? So let's say within an ecological niche, there is a mechanism that can be seen as optimization in terms of adapting to that niche.
I think I agree with you to an extent in that you can see it that way, but there's no optimal solution. And normally when we're optimizing, there's an optimality, and the algorithm's goal is to get to it. And that's just not a thing.
Right. So there might be a steady state for some period of time, but when there's a shock to the system, everything can change.
And so if our learning is like that, what does RL say?
Right. So you could look at it. Let's say the easiest way to formulate that would be to say there's a shift to the reward function, for example. And a lot of that people are starting to study that in the continual learning space. So you can formalize some aspects of this and say, well, what if the reward function suddenly changes? What if there's a shift in the transition structure in the environment? How could an agent, for example, adapt or deal with that? At the moment, that's in its infancy, right? From the machine learning perspective, we're only able to deal with that under very specific assumptions. So, for example, we can assume some kind of smoothness, that the reward structure only changes slowly over time, or that there's some other structure we can build in and anticipate. But yeah, I think it's really interesting to think about more broadly what those shifts and changes could be and how algorithms could adapt to a wider and wider setting.
So I'm a big fan of thinking about non-optimal solutions to things. But as you were saying that, Jovo, I wondered if maybe you could actually formalize a specific point of optimality for evolution, which is that all of the available energy in the environment is being used to replicate a particular set of DNA. Like, could it be? Is that a sort of form of optimality that you could frame in that way? Like, that's like a point that you're trying to get to. Like, there's an amount of energy, and you want basically all of the available energy to be used.
Sorry,
with this one particular genome. Sorry,
but like there are so many different kinds of DNAs in the same environment. There are so many, and they survive, and they have so many different lifespans. Like, in principle, there is no reason for us to have the lifespan that we have. Trees have some trees have thousands of years of lifespan. Like, I'm talking about this book again, but let me just I put this book close by because every now and then chapter 7.
What's this called?
It's called Other Minds. The octopus, the sea, and the deep origins of consciousness. So the subtitle is not great. but it has a lot of chapters. Chapter 2, chapter 7, there's a couple of chapters about evolutions, and also a chapter about and that's something that I was looking for, in fact, with the project for a project with Rob Shapar and Miro. I was looking at it for what determines the evolution of lifespan or time of death for species and for an individual. It's encoded in the DNA somehow, but what are the factors that come in? So some people had different theories, for instance, since the 50s and 60s, and that chapter describes it very nicely. Some people thought, oh, it's for the age of reproduction and managing that and managing populations, but then they discuss other species like trees, for instance, where it can live for thousands of years in principle. And in fact, the older it gets, it has more points of reproduction on its surface. So it's the opposite of the situation with some other of us some other of our species where supposedly reproductive capacities reduces. Then again, the gender differences. Then again, the having two genders, or like in this case, biological sex, not gender, for reproduction. And all of these things, it seems like there is no optimality for this. Nothing was being optimized. It just so happened this was a contingent path. And so, Brad, I think I would still go with the idea that it doesn't seem like something was being optimized in the DNA. Maybe there are local optimizations. For instance, maybe the touch sensors were being optimized, where there's something in the evolution of the hand that was being optimized to something at some point or adjusted to that. But even that, we can write it as an optimization problem, but it's unclear whether it actually happened with the optimization framework we are looking at it. I think it's maybe a homeostatic framework is better than a reinforcement learning framework, because something is trying to maintain some homeostasis within a given changing environment. And it has to, so it cannot maximize homeostasis. You can't maximize homeostasis because it's going to deplete constantly, and you have to move between different things. You have to move towards food. You have to come back and sleep. You have to protect your kin. You have to, there's all these things. There's no one thing you can do. And it's not like, all right, I will go and sleep for the first 10 years of my life and the rest of my life I don't sleep. I can't do that because there is a state I have to maintain with all of these, right? So I think there is something there that might be kind of another framework for this. So I've been reading a lot about the history of reinforcement learning recently, and especially, I think the introduction chapter of Sutton and Bartow, and then their chapter 13 and 14, which are about the psychology and neuroscience history that's underlying reinforcement learning, was very interesting. It's very much generalizing principles of learning that come from classical and instrumental conditioning. Just like it says, all right, let's take something that has worked out very well in some creatures. Let's simplify those learning principles, and then let's use these learning principles as a foundation of a lot of different kinds of learning, right? So because it's so simple, it can accommodate a lot of very different kinds of learning. But at the same time, there is a risk that maybe there are learning principles we're ignoring that are also in biological agents, right? And the field is like 50 years old. So, okay, sorry, 70 years old. I keep thinking it's 2000 for some reason. So the field is like, 70 years old. So it's not very old, We're not optimizing for a learning mechanism that's going to explain everything, but we definitely can explore various kinds of learning frameworks inspired by different principles of learning in biological systems.
Yeah, I mean, what I would say, listening to this is looking at the gaming work that you showed, Katja, and you've done. Mm-hmm. That there's no doubt in my mind that most intelligent behavior that one sees in animals, and there's a lot of intelligent behavior, mm-hmm. I think can be captured by, learning, whether one talks, and there's been a lot of discussion on this Salon about, learning across, different timescales, evolution versus within a lifetime, and, capturing them within one framework. I think it's true. I think that, when if you consider an animal mostly limited to its niche, then that niche can be considered a kind of video game, right? That niche has rules, it has structure, mm-hmm. right? And you need to learn the rules of your bit of desert you need to learn the rules. I think that's true. I think I think it would be really, like you said a while back, gutsy to think that you need to come up with anything else to explain a large amount of adaptive behavior within a niche where there are local and more global reward landscapes. I think it's true. My only thing is that I genuinely believe, as everyone knows, that humans found a cheat out of that. It doesn't mean that they don't do it, right? Just as we saw from Hugo the other day, I believe that, in certain situations, whether it's mazes or hotels, that we do what animals do. All I'm saying is that I still am convinced that we found a kludgy escape from that way of learning things, right? In other words, that was our evolutionary emergent thing, is we escaped the clutches of that kind of learning. We still use it, absolutely, but we do something in addition. In a way, what we do is a sticking out its tongue at the other animals that only have that way of doing things, right? Do you see what I'm saying? That we actually found an escape hatch, and that's called meaning, right? Which you discussed about. And so that's the view I take, is that reinforcement learning is true because it had to be defied. Right?
Interesting.
Right?
Yeah.
And that's the way
I see where you're coming from. Right. Yeah, I'm not fully convinced. Right, this touches on this debate of are humans fundamentally different from other animals, and I'm not convinced that's the case.
Yeah, but we're not fundamentally different. Just to say we are the same, except something else. Like the hand of a human is not fundamentally different from the hand of a chimpanzee, but it does have an extra feature that makes a huge difference. So it's a false dichotomy to say, are we completely different? But all I'm saying is that we got this extra sort of add-on, and I just find that very interesting. So that's a position that I still feel is that there's just an extra thing we've got that is a stick in the eye of this other way that animals are condemned to use. Right?
Yeah, and in a way that resonates with the way I see this research program as well, right? So, for example, in a game, could you start and try to identify certain behaviors, let's say aspects of learning, and try to see if we can replicate those? And every time you make progress on that, you can find something, okay, this is something we can't do yet. Can we figure out how to explain that? It's going to take a very long time until we get to the point of figuring out whether there's something else that allows us, let's say humans, to have that notion of meaning or that spark of originality. But yeah, long term, I think we can at least start to get to that answer, even if it takes hundreds of years.
One of the things that came up in the chat, Ella suggested the possibility to think about boredom as a mechanism for driving different kinds of creative and interesting behavior. And certainly, I mean, animals do play as well. Like that's something that kids do. And that's also sort of a driving force to sort of explore things, is sort of like looking to get away from what's familiar.
Fantastic. I see we have a new guest. Hi.
Thanks so much, Brad.
Thank you, Fred.
Should I go?
Zeno, it's been too long.
Yeah, it's been a little while.
Yeah, please go ahead.
I didn't really have that much to say, really. My main point was, it seems to me there's a difference between kind of thinking about optimization in the way that Jova was talking. So, there is the real world, things happen, and I can understand why all the creatures are the way they are by thinking of it as some kind of optimization process, right? And for me, that's the model of the world, right? The world isn't literally an optimization. It's a way in which I can capture and understand what I'm observing, versus when we build computational theories like RL, where we explicitly put in the kind of the constraint that our agents are supposed to be rational agents, which maximize some kind of optimization. And so my only point was that I think these two things are slightly different, right? In the second sense, we are enforcing some notion of optimality, whereas the first case, we're kind of observing it or some approximation of it. And I think if you take the first stance, then maybe Jova and John are not so inconsistent, right? Where we don't actually assume that there is some thing that's being optimized. I think that opens a lot more freedom to think about ways in which all these things that humans can do may not necessarily be tied down to some overarching notion of optimality, right? I think one of the things that's appealing about the RL framework is that you can say, okay, we're just trying to fundamentally optimize this thing, this goal, and all of these interesting emergent behaviors are somewhat indirect manifestations towards that goal. But I think that appeal is somewhat misleading, because you then have this other problem, which is like, okay, what is that thing that I'm just trying to optimize? Is this just there? This is a hard question, which is never really answered, because I don't think maybe there isn't an answer. So I guess, I'm saying many different things, but I think some of the appeal of RL may come with many different kind of fraught constraints, which we haven't really reckoned with.
Sorry, just to be clear, just for clarification and to be more, so I'm not sure why the first one is not a gateway to the second, even if one doesn't adopt a reinforcement learning framework. If you think that optimization can capture what you're observing in the world, on some level, you can then also capture behavior of animals as some kind of optimization. So I'm not, and RL is also, so I'm a little confused, because it's, if in any meaningful way you can model something as optimization, that's enough. Like RL is not a deeper philosophy about things, right?
Well, I guess, you can, but that doesn't mean you necessarily should, right? So I think if you think about the question that John was asking, should I think about all these creative acts that humans do as, necessarily part of some optimization process, right? The answer is either yes or no. And if you're tied to the idea that humans are fundamentally optimizers, the answer has to be yes. Whereas if you take this kind of Jovo stance, where optimization is just a model, the way that understanding the world, then maybe the answer is no. Like maybe I could understand the fact that I can be creative purely from a creative model, which doesn't have optimization at this kind of ground level, which is driving my behavior.
So am I right in that? Just trying to understand. So are you saying that maybe reinforcement learning is a model, it's an abstraction. We shouldn't take it literally, and there might be a lot of other things that people do that aren't explainable by the reinforcement learning framework. Is that roughly what you mean?
Yeah, I don't have that strong of a stance, but I think underlying many of these arguments is that fundamentally are all of these creative acts, and other things that we can do, are fundamentally driven by this underlying RL style framework. I think this is the question that's being brought up, and I don't know if that's true or not. And so I guess if that is true, then that needs to be justified in some way. Maybe that's my questioning and that I would pose to the group.
Right. I guess part of the question is, is reinforcement learning a model that can capture a lot of the biological learning that we see? To be clear, I wouldn't say it's a model of everything we do, right? We're specifically talking about models of learning. And within that, I think reinforcement learning is a very powerful model. I think there's a lot more we can explain with it than we currently have, especially when we combine reinforcement learning with maybe other learning mechanisms. It's not going to explain everything that we see in the world, or every behavior that we see. Yes, I agree with that.
It's another way maybe of phrasing what Zena's saying, and Zena, tell me if I'm wrong, is like you can approximate any function you want with a polynomial basis expansion, but doesn't mean you should, because there's lots of other things that work better, like deep learning often works better, or support vector machines. And so I think, Katja, one thing you kind of alluded to earlier is that maybe RL can be used to solve all of our problems. And I think Zena's point is that it can be used doesn't mean that it should be used, because there could be something else that also could be used and is more efficient or otherwise more tractable in some way.
Can I maybe make one comment here? So Jova, your perspective sounds like an engineering perspective. It sounds like, hey, there are some problems. Here's a toolbox of machine learning stuff I have, and I can use a bunch of this, and I don't need to use this. I could use this, right? Katja's version is a little bit more at this kind of agent learning level. So can we create learners that can do things in ways that are similar to the way humans interact in games, for instance, right? So it's a little more demanding than your case. It requires agents to have some kind of an internal architecture that's flexible enough. It requires a lot more lifelike features. That's not in just like a bunch of polynomials, because they can't immediately adapt. They need a lot of data. They don't have online versions, etc. So I think that you can look at things from an engineering problem where you can use some toolbox with machine learning tools and apply them. You can think about biological data as something that we want to model in general and make some predictions based on what we already have. That's another problem. You can do some work like, for instance, the Tenenbaum tradition, where you can create sort of some models that capture some behavior and make some predictions, but they don't have correspondence precisely, or in any not precisely, even vaguely, they don't have correspondence quite in brain architectures. Or you could go more towards models that capture behavior, can generate new behavior, and also have some correspondence to brain architecture. And you can get more precise there. And you can use learning principles that are very explicitly inspired by biological learning if you want, or not, right? I think if the goal is, depending on which goal one has, like just engineering goals, capturing behavior irrespective of the mechanism, correspondence to mechanisms of biocreatures goal, capturing behavior in a way that they interact. It's not just on tasks or classification, but it's actual behavior interactively with humans in games. That's a little bit, I think Katja's goal is pretty ambitious, and it's a very cognitive science type of goal, actually. And I don't think just any tool could achieve that. The tool would need to have learning capacities. It would need to have adaptive learning capacities, interactive capacities, and polynomials don't have that, right? So a lot of learning principles don't have that. A lot of data-heavy sort of learning principles don't have that. And then obviously the goal that some of us have is that we find computational learning principles and mechanisms and architectures that also not only correspond to human behavior, but also correspond to architectures, whether it's human or whether it's rodent, etc. So I think depending on these goals, we might be a little bit more constrained in what tools we can use, or what tools we should use, if since you use the should word, if that makes sense.
Mm-hmm. I think that's a really good perspective. And so just reflecting on that in the context of the kind of gaming scenarios that we aim at, it's very possible that there might be many, many different kind of algorithmic computational approaches to achieving the goal of, let's say, getting human-like coordination between teammates within a game. At the same time, the search space is very big, and we barely know where to start. So there are two sources that we can very readily make, well, not readily, but that are quite obvious candidates for making progress. One is the tools that we already have. The other one is try to find examples as much as possible in biological learning or biological organisms where we see at least the proof of it's possible to achieve that kind of behavior in such an organism. So I think that's a really strong case for trying to draw parallels with what might be happening in biological organisms. If there are many approaches that get us to the same behavior, then from the engineering perspective, we would prefer the one that is the most, let's say, energy or cost efficient. But at the moment, we don't really have that luxury. Any will do, as long as we manage to implement and run it and get the behavior out of it that we want.
But Katja, just to get to Ida's point and to Zena's about engineering, right? In other words, I do think that games are a bit more like an engineering problem. Like, for example, if I'm on one bank of a river and I have to get to the other bank and I have to build a bridge, right? And there are materials and there are, you know, Minecraft, like you have to build a bridge over it. That seems to me amenable to this kind of framework. But what about when you go, what's a river? Why is there a river?
A philosophical question.
You see, no, but there is. But scientists say, what's a river? Why is there a river here? That's a different kind of question to how do I cross it? And the idea that RL is going to answer, why is there a river here? It's just not going to happen in my view. Whereas to build a bridge across it, absolutely. But how questions and what and why questions are different. And I think what Zena was getting at is it's a perfectly legitimate question for a human to ask, which animals don't ask, which is, why is a river here? What on
why
earth
are we
is a
here?
river? Yeah, not just why are we here. There's an answer to what a river is and why there's a river here. It's not an existential question. It's a real question. But it's a different kind of question to how do I get a bridge over the river? And what I'm saying is that your framework, in my estimation, only answers how do I get a bridge across the river.
What if we combine the reinforcement learning framework with the notion of, for example, intrinsic motivation or curiosity that Ida mentioned earlier?
Plus,
in that,
Oh,
go ahead.
Sorry, just wanted to say to John's points, like, I feel like a lot of the times John asked something that, like, there has been workshops at ICML where people are doing that, or people I know are working on. So the idea of reinforcement learning using intrinsic motivation to explore has been around for a couple of days now, and it has had so many iterations. But then there is the other direction, which is reinforcement learning agents asking themselves questions in order to navigate, in order to explore. So, for instance, so one thing that we talk about as an example is, if you go to the kitchen and there is no knife and you really need to cut something, you might look for another sharp object and treat it like that, right? So, or it could be that the agent comes back to an environment it's been trained in, and all of a sudden there's something, and it should say, why is this thing here? So I might need to explore around to figure out if somebody brought this here, for instance, right? It's not as, X factor as you think. That's what I'm trying to say. And there are people who are really working towards that, towards an agent that asks itself questions in order to explore the environment, an agent that uses language in order to update its world models, an agent that explains its world model in languages. I had a meeting today about these issues. That's part of the reason I'm saying there is a difference between, in principle, being not answerable question versus I haven't seen the work so far, right? I want to make sure that we don't cross that bridge too soon.
Well, when I see a definitive answer, I will believe it.
Yeah, it's a really interesting set of questions. I also like the perspective that James is putting in the chat here about causality. I think that's a really fascinating topic, and questions at the intersection of causal modeling, causal structures, and reinforcement learning. If you had an agent driven by, let's say, the desire to explain its world, if it had causal models, then the question of why is this here, right? Expecting causal structure in the world could potentially give rise to the sort of questions that you mentioned there. Our agents certainly don't ask that at the moment. I think it's not impossible to get in that direction, and I think there's some fascinating work to be done in that space.
It's interesting to me to see, like, on the one hand, I feel like John is saying the onus is on RL people to prove that it can do this kind of thing. And then the RL people say, no, actually, the onus is on John to prove that it can't. And, I don't have an opinion either way. I just noticed that you
good
say
observation.
different things.
Well, I mean, I think I said it the other day in comparison to the Gettier examples. We want to, so in the Gettier examples, you could make a guess about something, make a statement about the world without the justified knowledge, and it might accidentally turn out to be true. That doesn't mean that you knew something. That doesn't mean that that was a justified stance. I think in order for us to be able to say something meaningful, we would need to have justified reasons. We provide our justified reasons why this is in principle. Oh no, we lost David Murphy. I think maybe their Wi-Fi went away. Hopefully they'll come back. So David Murphy, if you hear us, please join us. But at the same time, if we don't cover the basis to have justified reasons for a claim, I'm not sure if it's comparable to a claim that's based on justified reasons, right? I think that's the place where I might disagree with you, Jogo, that this is a, both sides are equal kind of situation.
The justified
I wasn't saying
reason,
both sides
the
are equal.
justified, no, the justified reason at the moment is entirely empirical. Is humans can do things right now that far out more than what other animals and computers can do. That is an empirical fact. And I say over and over again that there are secret societies working on all this. But until we actually get an empirical result that we can see that equals the common sense, language-based, creative, open-ended science answering that humans do, then I keep my case. So just show me the equivalent in creative common sense in a computer that is equivalent to Go and Atari, and I rest my case.
I
But
first want to
empirically,
appreciate,
it has not happened.
John, I want to first appreciate the SAS. I feel like every time that knowledge lacks, SAS increases, and that's fantastic to observe. But no, let me finish. While I appreciate the SAS, as secret societies might be meddling with your Wi-Fi, I'm not sure. Maybe you need a tin can for that. But the people working in this field is not secret societies. It's a lot of departments. It's public. We give public talks. We publish our works, etc. So reading them would be a requirement of making a statement. Or let me finish. No, let me finish.
I don't need to read them. I saw Go beat Guy Sadol. I saw that.
So let me finish what I'm saying, because like I haven't finished my sentence. We have this rule at the Salon where we don't interrupt, right? Even when we get sassy, we still don't interrupt. So what I wanted to say is that I agree with you that there is an empirical way of assessing these things, and I agree with you that empirical that empirical state hasn't been achieved. However, the claim that I am questioning here, using the Getty example, is the claim that, therefore I can't. So it's like, okay. So it's basically similar to somebody says, hey, here is my grant, and they have a 5-year, 10-year plan that is under grant, and you keep every day saying, oh, you still can't. And you're like, yes, this is the grant. It's not yet. This is the plan, right? This is not in principle not doable.
Never said to be, so we are clear once and for all, I never said, and you're absolutely right, it would be wrong if I did, and Katja has also made the same statement that you've made, that it never will. I mean, that would be absurd, right? What I'm saying is that there's a difference between a kind of example where you go, oh, that's on the way, right? Versus saying that conceptually, there is grounds for optimism that we will get there. I completely concede that to you. You're absolutely right. All I'm saying is that there seems to be a genuine challenge, a real gap, where we're just not making the empirical headway that one would hope that one could make given the conceptual possibility. And all I'm asking completely empirically is what's causing the gap? Why are we still more like animals than like humans? What are we missing? And I think that's all that Zena was also getting at, and he and I have talked about this, is it just tincture of time and we will simply get more sophisticated and we'll get there? Perfectly possible. Or are we missing something qualitatively different? And all I've said at all these salons is I haven't heard anything that breaks that tie yet.
Very interesting. To me, there's just such a difference in terms of the scale of anything that we would currently feed into a reinforcement learning agent. There's no, like at the moment, technically, I don't think we're in a position to even put that comparison on a reasonable footing. But if you think about the richness of the world that we grew up in, compared to even an agent playing a couple 100,000 hours of a video game, it's really, really impoverished. So we cannot even hope to make any progress on getting those agents to show the kind of meaningful language-based interactions that we're talking about. The
Gettier case that I was getting at, this idea of being right by accident, that the garden shed doesn't have a rake in it, behind your back somebody puts one in and you go, there's a rake in the shed, and just by pure accident you were right, even though you had no real reason to be right. It would be absolutely true that it would be Gettier to say that the perceived empirical gap right now is because I know that RL will never get there. That would be, if it turned out one day to be true.
Fair. Yeah.
But I do think that there's a sort of creeping optimism that somehow we'll get there. And I would just like to see that. That's all. And I just think that we have to be open-minded, that maybe we have to add a new spice or ingredient that we haven't discovered yet scientifically. And I don't think that's bloody minded. It's just an intuition.
No, that's a good point. So John, as you know, as I said like half an hour ago, I do think there are other learning principles we might be missing out on, and we might need to sort of incorporate in order for us to have better learning frameworks also. But I also agree with Katja that at this point, the comparison is not a fair comparison yet, because we are very far from having the level of enriched life for our agents that humans get to enjoy in terms of how much training they get and how much sort of evolutionary information has been passed on to them via the DNA and the architectures of the brain. We're just not anywhere nearly close, right? And I think John, sorry, go on.
Oh, go ahead. Finish your thought.
I just want to say that brings us to the John Langford slide that you really liked, John. The slide with the worm and the spider, and saying that when he was saying we are not convincingly further up than, like, you know.
He said, what did he say? He said basic RL is the worm and advanced RL is the spider, right? And then there was a wolf after it, right? And I just think it's an interesting thing. I just think we mustn't, I think we just have to be pluralistic. And I think sometimes, you know, because it's such a great algorithm, you know, RL could potentially be the master algorithm. It could be the ring that rules them all.
Oh, don't say the master algorithm, because it refers to a very not acceptable person's book. So that's the title of somebody's book.
Oh, is that right? Well, that was me. That was a Getche mistake.
Let's call it the main algorithm. Main algorithm.
Right. So
I wanted to come. What that book is.
Just to respect David's time, he's been on screen for a bit, so I just want to make sure that David gets to ask his question while we continue this. David, go ahead. Oh, you're muted. Unmute. You're muted.
It's still muted? Okay.
No, it's perfect.
Thank you, Katja, for the interesting talk, and thank everyone for the conversation. I think my question seems a little bit mechanistic, actually, compared to the discussion we were just having. But what I wanted to ask you is, it seems in many of these team cases, whether it's a team of RL agents or a team of humans and agents, that the agents are quite passive in how they observe and then they make decisions. And I'm wondering if you have thought about and might share some of those thoughts on where an agent might actively take action in order to perturb another agent to gain a better understanding of those agents' goals or intentions, and therefore perform better.
That's a fantastic question. And in a way, it's really at the heart of what we're trying to test out in that bleeding edge scenario and algorithms like Maliba that I was showing. In the first demo, so showing the agents in the game, those were all reinforcement learning agents that had been trained together in self-play. And so they had learned to coordinate. In a way, it's like there's a very fixed protocol for them to interact. There's no need, in a way, for them to probe, because they, in a way, know what to expect. If I do this, then the other agent is going to do that. It's very mechanistic and, if you will, passive. They don't need this probing type of behavior. What we're trying to achieve with Maliba is the underlying framework is a Bayesian framework that allows the agent to learn an optimal policy with respect to its belief over the other agents. And so in principle, this would allow the agent to learn a policy that is exploratory to the degree that you describe. It might be optimal in a given situation for the agent to take a probing question in order to understand what opponent or teammate it's interacting with in order to have that optimal behavior. And in simple scenarios, we're able to show that that works. Of course, that is, again, a far cry from the kind of intricate interaction that we see with human players. But I think in principle, that notion of having kind of powerful architectures that can capture complex distributions, uncertainty, about components. That is one of the building blocks that we think we'll definitely need, but a lot more understanding and additional components will be required to solve those more complex scenarios.
So if I could just clarify something. So in effect, this agent then has to have some belief about what the other agents have in mind and test whether it's, Ida reminds me, I used the word hypothesis, test whether those hypotheses about the other agents' minds is correct or not.
Yeah, and at least in principle, that's the kind of structure we're trying to build into the agent, right? So it's the ability to maintain complex beliefs over the other agent type and their current mindset, if you will. And then the ability for their behavior policy to take in, so be conditioned on that full distribution over the current agent's beliefs over the other agent. Those are some of the building blocks that we believe are necessary for achieving that active probing behavior. It's probably not all.
Okay, and I'll ask a even more mechanistic question, if that's okay. I just saw this slide of your architecture. I haven't read it, so I apologize if I got that wrong.
No worries, of course.
But you were describing that it uses an autoencoder to learn that. So in the case where you have multiple agents, would you need to have a resource problem here of having multiple autoencoders and be limited to a certain number of slots of agents who you could actually track? Or are there other approaches where you're not so limited?
That's a fantastic question. And yes, that is a limitation of our current approach. We can take agents up to a fixed number of slots, and those would be processed in a batch in parallel. We haven't conducted any experiments where the number of other agents would be flexible. Coming up with an architecture that would have that flexibility is a really interesting question. It's not something we have solved.
Okay, great. Thank you very much.
Thank you.
So being mindful of time, it's 6:25, and I just want to read one very highly voted question, which might be related to John's comments also. Mathis Pink asks, have you considered modeling something like joy in RL agents beyond examining the reward return itself? I mean, joy in game does not just depend on reward, but also substantially on its interplay with the perceived difficulty and with surprise in particular. And a lot of people, I mean, no, not a lot. There's 3 comments on that, which I'm not going to look too much into the comments, but yeah, if you have any answer to that.
It's a fantastic question. It's not something we have done. In order to make progress on that, I think we even need a better understanding of what joy and enjoyment mean for a human player. When we talk to people who develop games, they say it's they know it when they see it. I think it would be a really interesting research program to make progress on that. I'd love to collaborate on that. So if that's something you're working on, do let me know about work in that space.
I want to just respond to one thing that John said in kind of in support of what Ida and Katja have been saying. And I think, no one has done an adequate job of the following. You start an RL agent with all of the intuitive physics and intuitive psychology and everything that a human baby is born with, and then provided the rich environment of the first, however 15 many years of our lives, and then you try to teach it Minecraft. And as far as I can tell, if you did that, it would beat all the humans. Right? Or maybe not, but there's really no particularly strong evidence either way. And so this question about like whether RL can do that or this, I think is a little bit, I'm not sure how to even answer it. There's the other set of questions, like John is saying, like, why do rivers, or why are we here, is a question that Katja said. That it's not at all clear how to even formulate in RL terms, and maybe Ida knows how, but I think it's almost more of a philosophical question than a RL/optimization question. Once someone figures out how to formulate it, maybe RL will solve that just as quickly as we do too.
I agree with your point. I wanted to come back to there's a reason that within my team we're not trying to explain those phenomena, right? Our goals are much more pedestrian. We're trying to get agents to behave in a specific way within the context of a video game. So we're not trying to make that claim that reinforcement learning could approach the learning or the complexity of human behavior in a less restricted setting. And I think it comes back to the kind of question we discussed earlier: why are games so useful for this kind of research? Because one aspect is that they exactly let us focus on a smaller aspect of the problem. So, for example, if I could show that an algorithm can learn to navigate a maze it has never seen before as quickly as a human that is seeing that maze for the first time, that could be really interesting. So we can ask questions about the speed of learning in very specific tasks without having to solve those deeper philosophical questions. And I think we need to make progress on those maybe building blocks first. Kind of a question to me is, how do we carve out building blocks that allow us to make progress towards those longer term, bigger questions, while still making progress in the shorter term?
Thanks. I think that's great. And what other thing could we do? That sounds like exactly the right thing to do, despite John's reservations about it.
I think John's question.
I don't have reservations. I don't have reservations, about Katja's work. On the contrary, I'd like to get involved. I find it fascinating, actually. I just feel like there's a difference between, our games, the unbelievable environment within which you can show how problems can be solved in a structured, constrained way, or can we go to what I'm asking is, can all of life be considered a game, right? When does life go beyond being a game? And when it goes beyond being a game, does it need new explanatory equipment for when it goes beyond being a game? And I think that's just the meta question. And I think games are already fascinating enough. And just one other point, if games are like niches in the world, and RL is closer to the brain machinery, and I think it is, then that is a huge amount of biology that you've done if you use the formalisms from game learning to explain how animals exist in niches across evolutionary time and in their own lifetime. I mean, that's huge, right? And so, in other words, it depends what you're thinking. All I'm saying is that evolution came up with one last trick, and that last trick is defying us. And I just find that interesting, but it could also yield. That's all.
Sounds like a perfect conclusion.
You muted yourself.
I just wanted to say thank you for coming. I think it's so cool that Wittgenstein is 2 miles away from you.
I'll tell him you say hi next time.
Yeah, thank you also for braving this late hour. It's by now 11:30 there, and we should let you go before it gets midnight and like your camera turns into a pumpkin or something.
I can put on my pajamas and come back for the second session.
That's a great idea. We should do a pajama.
Yes, we'll have to send you some dolphin pajamas.
Dolphin.
We've had a kind of a dolphin theme going on right now.
Oh yeah, okay. I'd love to see those dolphin pajamas.
What is your favorite animal, actually? Because
I like penguins.
Okay, so it has to be penguin this time, John.
We're gonna have to make a penguin, actually. I don't know if you've ever seen that little GIF where the penguin gets up and blasts somebody, and then it sends a missile just to finish them off. It's one of the greatest sort of.
I haven't seen that one. Please send it
to you,
I haven't seen it either.
Yeah.
I'd love to see that.
It's the ultimate video game penguin.
There we go. Fantastic.
Excellent. I'm going to check that out.
All right.
On that note, again, thank you so much. Thank you, Claire and Eva, for helping us in the beginning with the technical difficulties. And also, although not all of us might think that humans are a trick, that are defying us. I think these discussions and the disagreements are extremely important. I personally enjoy them. I think even the emotional moments within them just mark the memory so that we remember, oh, the day that this happened, right? I feel like there is a lot of these kinds of narrative devices that we use in the salon, like in an emergent and non-goal directed and non-optimized way, that hopefully will help us remember the discussions, will help us have a continuity, and helps us basically stay awake after a whole day of meetings in the middle of a pandemic, staring at a laptop. And I really want to thank everyone who participated in the chat. And sorry about those who didn't get to. We didn't get to 3 questions were I think unanswered still. And we will hopefully we will send them to Katja in case you could follow up with her, or if you wanted to, you could follow up. Yeah, thanks again, everyone. Thanks also, Brad and Kanaka. And thank you, Katja. Bye-bye.
Bye.
Thank you for having me. This has
Thanks,
been a lot
Katja.
of fun.
It was a pleasure to have you.
Thank you so
Thank
much.
you.
Bye.
Bye.
Have a good night.
Thank you.